Hello everyone. Today we're on to more related rate problems. We're going to take a look at some examples involving trig, so let's get started. First question of the day. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's angle of elevation is pi over 4. The angle is increasing at a rate of 0.14 rads per minute. Determine how fast the balloon is rising at that moment. So to start, it would be helpful to identify some things that we know and something that we need to know. So we know for sure that this distance is 500 feet. It's usually a good idea to start by drawing a diagram. We can call this balloon height h. This is a right angle as it's a level field, d theta dt. At the moment, the angle of elevation is pi over 4, is 0.14 rads per minute. So we need to determine how fast the balloon is rising at that moment. So we want to figure out how quickly this variable is changing. So what we ultimately need to know is dh dt at this angle. We can start with chain rule. If we want to know what dh dt is, we can break it down in terms of dh d theta and d theta dt. So when these are multiplied together, these d thetas essentially cancel and we're left with dh over dt. The way that h is related to theta is with this right angle triangle. Tan theta is opposite over adjacent, which is 500. And we can just maybe get that all on one level. H is 500 times tan theta. Next we need to know dh d theta. We already know d theta dt here, so that piece we have. We need to know this one. So what we can do with this equation, because we know how h is related to theta, is take the derivative of the whole thing with respect to theta. So the derivative of tan is sec squared. So now we basically have everything that we need. We have dh d theta here. We have d theta dt given in the question. So it'll be dh d theta, which is this, multiplied by d theta dt, which is 0.14 rads per minute. We know theta at this point is pi over 4, and we know sec is defined as 1 over cos. So sec squared theta would be 1 over cos squared theta. At pi over 4, cos theta is 1 over root 2. And if we square 1 over root 2, that's a half. And if we do 1 over 1/2, that's the same as 2. So what we can do with this sec squared theta is just let it be 2. So now we do 500 times 2 times 0.14, and that's again rads per minute. So when we do this multiplication, we get 140 feet per minute, and that's the final answer. That is the rate of change of the height of the balloon as it's lifting off. So on to the next question. A boat is pulled toward a dock by a rope through a ring on the dock 6 feet above the bow. The rope is hauled in at a rate of 2 feet per second. So the first thing we need to figure out is determine how fast the boat is approaching the dock when 10 feet of rope is out. So it would be helpful to draw a diagram, as I have done already, and identify some things that we know. We know that this length is 6 feet. We know that the rope is being hauled in at 2 feet per second. So we could say dr dt is 2 feet per second. We can maybe label this as x between the boat and the dock. We need to find dx dt when the rope is at 10 feet. So this is a right angle triangle. X is related to r by Pythagoras Theorem. So we can start by going x squared plus 6 squared equals r squared. We need to get dx dt out of this equation. So what we can do is do implicit differentiation to this and see if we can isolate for dx dt. So we would get 2x dx dt plus the derivative of 36 with respect to t is just 0, and the derivative of r squared with respect to t would be 2r dr dt. Remember, we need to do the chain rule. So dx dt is what we need to find out. We have r, that's 10. We have dr dt, that's 2. And we need x. So at the point when the rope is 10, we need to use Pythagoras Theorem, 10, 6, and x. So we would do x squared plus 6 squared equals 10 squared, and we'd eventually get x squared equals 64, square root both sides, x equals 8. So we just sub that in for x there. So now we just need to sub in everything we know and solve for dx dt. So we would get 2 by 8 by dx dt equals 2 by 10 times 2. So I guess we could divide both sides by 2 and then divide both sides by 8, and eventually we would get dx dt is equal to 2.5 feet per second. And that's the final answer for part A. So moving on to part B, we need to determine the rate the angle between the rope and the dock is changing when 10 feet of rope is out. So we should identify the angle there. We need to figure out what d theta dt is when r equals 10. So to start, we need to figure out how theta relates to the other variables. So one thing we can do is relate using cosine. So we could do cosine of theta equals adjacent, which is 6, divided by the hypotenuse, which is r. And then we can get it all on one level and just do this, and then see if we can get a d theta dt out of this equation. So let's do that now. We need to do the product rule on this and take the derivative with respect to time. So the derivative of the first would be dr dt, and then just multiply that by the second. And then we need to add the derivative of the second times the first. So the first times the derivative of the second would be that, and then we need to do chain rule, d theta dt, and the derivative of 6 with respect to time is 0. So dr dt we have, that's 2. Cos theta we'll need to figure out. R we have, that's 10. D theta dt is what we need to find. And then we just need to figure out what cos theta and sine theta are. So we can use the definition cos theta is equal to adjacent over hypotenuse. So 6 over r, that's adjacent over hypotenuse. And for sine is defined as opposite over hypotenuse. So that would be x over r. And we know r is 10 in this case, and x, as we found out earlier, was 8. So now we just need to figure out d theta dt by making substitutions here. So dr dt is 2. Cos theta is 6 over 10. Subtract, so I just brought this negative sign out front. Subtract r, and then sine theta is x over r, so that's going to be 8 over 10. And then we need to solve for d theta dt. After some work, we'll eventually get d theta dt is equal to 12 divided by 80, which is equal to 0.15, and that's going to be units of rads per second. So on to the next question. Two sides of a triangle have lengths of 15 meters and 20 meters. The angle between them is increasing at pi over 90 rads per second. We need to determine how fast the length of the third side is changing when the angle between the sides is pi over 3. So I've already drawn a diagram here. We'll call this side 20 meters and this side 15 meters. Those are fixed. The angle between them is increasing, and as a result, this other side length is also increasing. So we could try to make a right angle triangle out of this and come up with a relation between the variables we need that way. But there's probably a more straightforward way to do this using the cosine law. So we're going to go ahead and get rid of that, and we're going to see what we can come up with using the cosine law. So I'm going to call this side C, and this is going to be capital C for the angle, and these are going to be the two known side lengths. So subbing that information into the cosine law, I'm going to get C squared equals 15 squared plus 20 squared minus 2 times 15 times 20 times cos of theta. Why not? Or capital C. I'll just use theta so it doesn't get confused with the lowercase c here. Alright, so that's helpful. Now we have a relation between the side length and the angle. Let's figure out what else we know. So the angle between them is increasing at pi over 90 rads per second. So d theta dt is pi over 90 rads per second. Determine how fast the length of the third side is changing when the angle between the sides is pi over 3. So what we need is dc dt when theta is pi over 3. So if we simplify this formula a little bit, we eventually get c squared equals 625 minus 600 cos theta. And we need to get a dc dt out of this. So we can do implicit differentiation to this equation. So we would get 2c dc dt equals 0 minus 600 negative sine theta d theta dt. We don't quite know what c is yet, but we know what the angle is at that moment. So what we can do is actually use cosine law here before we took the derivative of it and figure out what c is when cos is pi over 3. So we need to sub in pi over 3 for theta. So we would eventually get 325 for this because cos at pi over 3 is 1/2. So we would do 625 minus 600 times 1/2. So then eventually c is root 325. So now we know what c is. We need to figure out what dc dt is, so we need to isolate for that. We can figure out what sine at theta is because we know what theta is. And sine at pi over 3 is root 3 over 2 based on our unit circle. And we know d theta dt is pi over 90. So let's make those substitutions. So now we need to isolate for dc dt. We can divide both sides by 2 and root 325. So I'll leave it up to you to show that we eventually get to pi over 39 rooted, and we can rewrite that as root 39 pi over 39 meters per second. And that's the final answer. So on to the last question. I'm going to leave this one for you to do. A beacon located at a perpendicular distance 300 meters from R on a straight shoreline revolves at 1 revolution per minute, and you need to determine how fast the beam sweeps along the shoreline at the point 400 meters from R. So here's a diagram for you that you may find useful. The distance between the beacon and the shore perpendicular is 300 meters. The distance between R and the beam location that we're interested in is 400 meters. And I'm going to leave it to you to prove that dx dt when x is 400 is this number. So I will give you one hint, well, a couple hints. How many rads is equivalent to 1 revolution? That's your first hint. And your second hint, in order to maybe give you some help visualizing the problem, is I've provided you with some sort of simulation in Desmos, and I've provided a link in the description, which hopefully you may find useful. So that's it for today. I'll see you next time.